This is it. This is the beginning. Our first real lecture about direct current circuits. In a lot of ways, this is the most important lecture of the entire semester, because without this lecture, you'll be missing the language that we use to communicate. So like I told you guys before, I assume you know nothing when we start this, so maybe this is a review for a lot of you, but I'm not going to assume that. So what we're going to cover is essentially quantities and units, something called scientific and engineering notation, and basically how we communicate values to other people. And a lot of times people think this makes our lives more difficult, but as you'll see, everything we're learning today is to make our lives easier. And so let's get started. First, with units of measurement. Okay, so in all of engineering, with the exception of those crazy civil engineers sometimes, we use something called SI units. Now, most of you are probably more familiar with the term metric. SI and metric are very close. They only differ in a few places. And we have things like length. And so normally in class I'd ask you, what is the unit of length? And you would all scream out, hopefully meter? Yes, meter. So we have two ideas here. We have the unit, meaning the name, and we have the symbol we use to represent it. So if I wanted to say something was 5 meters, I would write 5 and then the symbol. Next up, we have mass, which is the only one that doesn't make any sense to me. Mass is actually a kilogram. I say it doesn't make sense to me because you'll notice it has a prefix of kilo. We're going to talk about that in just a few minutes, but we got to do it because the SI people said we have to do it. Time, you should all know this one. Seconds. Electric current. So these are some of the ones that are going to be important to us this semester. Anybody know it already? Try to guess. It is amperes. So you're going to see that voltage and current are different. And for current, our symbol is amperes with an A for the symbol. Temperature. This is where it differs from metric. It is not Celsius, it is actually Kelvin. So Kelvin and Celsius are pretty similar. 1 degree change in Celsius is exactly the same as a 1 degree change in Kelvin. The difference is what they consider zero. So in Celsius, 0 is the freezing point. And in Kelvin, well, let me try that. I misspelled freezing. That's bad. And in Kelvin, 0 is literally the theoretical coldest it could ever be in the universe. So 0 is actually absolute 0. So in Kelvin, in my current office, which is in my apartment, it's about 273 degrees. Luminous intensity. And there's some debate about this one. You will find both in use. Technically candela, but lumens also sometimes get used. And amount of substance, we won't be using that very much at all in this course, but it is the mole. So if you're going to memorize some, what we need for this course for sure is electric current. The rest we won't use all that much, I guess seconds, but hopefully you already know seconds. And again, these are some of the ones you'll learn throughout the next year. Not all of these now. We said current was amps. Charge, which we will use in next lecture. Coulomb, with a C. Voltage. This is a toughie, guys. If any of you miss this one on the test, I'm going to be very upset. Voltage is volts. And again, the symbol is a V. Resistance. We covered this already. You might not remember, but we covered it. It was in that history lecture. Ohm for Simon Ohm. And notice that this here is not a regular letter. That is from the Greek alphabet. It is the letter omega. And so that's how we represent ohms. So if I were to say something was 5,000 ohms, I could say 5 kilo ohm. Power, watts. So these are the ones that you absolutely need to memorize like today. We will use all of these within the next week. These are the ones we really want to focus on for DC circuits. I've got some other ones here. We're not going to go through them too much in depth. These all have to do with magnetic fields and things like that. You will use these, but they're going to come up next semester in alternating circuits. Alternating current circuits. Alright, scientific notation. So before I jump into scientific notation, I told you I'm going to start from the very beginning. I'm assuming you know nothing. We need to start with exponents. Anybody know what an exponent is? Let's say I have a number like 10. Right? If I were to put something up here, like that, this would be the exponent, that right there. And this would be my base. And what this says is, take the base, and raise it to the exponent, the power number of times. So in this case, there's only one, so I have just 10. If, however, I had something like 10 to the 2, I would have 10 times 10, which is equal to 100. If I did 10 to the 3, well, that would be 10 times 10 times 10, or 1,000. And we can have negative exponents too, right? If I had something like 10 to the negative 1, what that means is I do the same thing, but I put it under 1. So I have 1 over 10, which is the exact same as 0.1. If I had 10 to the negative 2, well, that's 1 over 10 times 10, which is the same as 1 over 100, which is the same as 0.01. Now the 10 powers are really nice because notice, if I take a number like 5 and I multiply that by 10 to the 2, notice because 10 to the 2 is 100, that's the same as 5 times 100, which is the same as 500. And so notice by doing it times 10 to the 2, I've taken my decimal point, which is there, and I've moved it over by exactly the power of the exponent. We're going to use that in just a minute with scientific notation. And so the idea behind scientific notation is that we want to take a really, really big number and represent it smaller. Or we want to take a really, really small number and represent it using less digits, I guess. And let me give you a better example. Let's say I want to give this number over the phone. 1327. Right? That would be a hard number to convey over the phone. I'd have to be like 132700000000000, right? That's not ideal. And plus, if I were to give you this on a test, you'd have to count the number of zeros like 5 times, enter them into your calculator like 5 times, trying to make sure you don't miss a zero. This is what scientific notation is for. We only have a few rules in scientific notation. Basically, we want to take the decimal point, which would be here, and we want to move it over so that to the left of the decimal spot, there is only one digit, and it can't be a 0. So let's do the example I just gave you, right? If I want to move this over, I need to move it over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I had to move that over 15 times. So I can change this to 1.327. Now, I can't just leave it here, right? What if you had this much in your bank account? Well then, hello, Mr. Bezos, I'm glad you're taking my course. But unless you're him, right? If I were to say that, no, you don't have this much anymore in your bank, you have this much in your bank, you'd be really upset, right? So since we made this much smaller, we need to balance it out with something. So to do that, I do 10 to the 15. And remember, by doing 10 to the 15, once I multiply these two, it moves the decimal point to the right, 15. Now, some students have trouble remembering. Do I move to the right or do I move to the left? Well, remember, when we're setting it up, we have to move the decimal so that there's only one digit to the left of it. And then when we pick the exponent, we need to do it so it's balanced, right? If this went from really, really big number to a really, really small number, comparatively speaking, then I need a big number here to balance it out, like positive 15. Right? So let's look at these examples here. I move this over 1, 2, 3, 4, so it becomes 1.2 times 10 to the 4. This one, 1, 2, 3, so it becomes 1 times 10 to the 3. This one is already in scientific notation. There's only a 1 to the left of the decimal. Let's try a few more examples. In this case, we have a really, really small number, right? But it works the same way. Notice I need to move the decimal over. So I move it over 1, 2, 3, 4, 5 times. And so that's going to leave me with 2.7 times 10. Now here's the thing. This number went from really small to much bigger. And so to do that, I need to put a 5 here, but it needs to be small so that it balances. So when you go from small to big, you need this to be negative so that it balances out. In this case, 1, 2, 3, 4, 5, 6, 7. So we have 4.7 times 10 to the 7. And again, this needs to be positive because we went from a bigger number to a smaller number. One more time, we need to move this over just by 1. And so we have 6.05 times 10 to the negative 1. Because again, we went from small to bigger. And that's all there is to scientific notation, right? It's much easier to read a number like this over the phone than it is to do something like we saw before. We got it? We feel good? We all understand scientific notation? I can't hear you, but I'm assuming you're saying yes. If the answer is no, go back and watch that again. It's a video. You can watch it like 5 times. Alright, so now that we've covered scientific notation, I am happy to inform you that in engineering we never use scientific notation. I know what you're thinking. I promised I would never teach you anything you don't need, and here I am doing it on the first day. First real day. No, we do need to understand how scientific notation works so that we can do engineering notation. So here's the problem. We don't like this either, right? I don't like saying this on the phone. 4.7 times 10 to the 7th? That sounds weird. And I for sure don't want to put this on a product advertisement, right? You have 4.7 times 10 to the 9 bytes. That's not snazzy. Instead, we want to use things like kilogram, or megahertz, or gigabyte, right? Or gigabit in that case, gigabyte. We want to be able to use a prefix instead of having this ugly 10 to the something. The problem is if we use scientific notation, since it can be 10 to the 1, 10 to the 2, 10 to the 3, we'd have to memorize like 20 different prefixes. We're engineers. We're lazy. That's like our job description, is make the world lazier. Make everything easier. So instead, we use engineering notation. It works exactly the same. The only difference is this exponent can only be multiples of 3. So it can be 0, it can be 3, it can be 6, it can be 9, it can be 12, but it can't be 5. It can't be 7. Only powers of 3. It can be negative 3, negative 6, negative 9, and so on. And so the way that you want to do this is instead of counting by 1s, just count by 3s. So let's do this example here. I've got move it over by 3. Now, I can't move it over by 3 again because remember, we still have to have something to the left of the decimal. And I didn't point this out. Because we're moving it by 3s, instead of only having 1 digit to the left of the decimal point, we can have anywhere between 1 and 3 digits to the left of the decimal point, since we're moving by 3s. And so I moved it over by 3. Again, if I move it over by 3 again, I'll have a 0 to the left, and we can't have that. And so we're done at this point. We have 12.1 times 10 to the 3. Again, I'll do it again. Move it over by 3. Move it over by 6. I can't move it anymore, or I'll have a 0 to the left. So I have 1 times 10 to the 6th. Last one. 25.4. Since this is 1 to 3 digits, right? It's a number between 1 and 999. It's already in engineering notation. And so we're done. Let's try that again. In this case, we're moving to the right. So I go by 3. And I can't stop, because if I stopped, I would have 0 to the left of the decimal. So I do it again. And now I have 1 to 3 digits to the left of the decimal, right? A number between 1 and 999. So this would give me 27 times 10 to the 6th. But again, notice we went from really, really small to much bigger, and so I have to be small to balance it. This case, 3, 6, and again, we can't go anymore, or there'd be a 0 to the left of the decimal, and so we have 47 times 10 to the 6th. This one, move it over by 3, and we're done. Number between 1 and 999, so we have 605 times 10 to the 3. Again, we went from small to big, so this needs to be negative to balance it out. And that's it. That's everything you gotta know. In this class, we will use engineering notation. Again, remembering that it's the exact same as scientific, only we only go by powers of 3. Multiples of 3. Okay, so the next thing I want you to know is you need a calculator. Don't do this stuff by hand. If your math teacher doesn't let you use a calculator, that's fine. But in my class, you will always use a calculator, right? I want you not to make mistakes. In engineering, we just want the right answer. So what I want to do is, first thing, buy a scientific calculator. It's going to make the next 4 years way easier. You don't need a graphing or anything fancy. For sure, not until year 3 or 4. It won't even help. But you want a regular scientific calculator, and please spend 10 minutes to learn how to use it. It will make it really easy. If you get stuck, come see me. I'll help you with it. I'm going to show you on the Windows calculator, which isn't ideal, but I don't really have another calculator to show you with. What you want to do is when you see something written like this, 25.7 times 10 to the 3, or you see something written like 25.7 E3, here's how you want to enter it into your calculator. You don't want to type it just like this. Let me pull up the Windows calculator. And you need to make sure you're in scientific mode. So over here, you can switch it to scientific. Like I said, don't use the Windows calculator. It's going to make you slower. Just get a regular calculator. They're like $10 or less. So if I want to enter this number, no matter what calculator I'm using, I will enter 25.7. And now I'm going to hit this EXP button. On some calculators, it'll say EXP just like this. Some will say E. Some will say EE. Just don't confuse it with the natural logarithm E, not this E. It'll just say EXP, EE, or actually sometimes it'll also say X, 10XY, I think sometimes. So anyway, we hit it, and then we hit 3. That's it. We're done. And so now if I wanted to do that number times 2, I could just do multiplied by 2. That's all there is to it, but you really want to learn this because we're going to be using it a lot for the next, like I said, multiple years. If you have questions, you know how to reach me. Just get a hold of me. Actually, let me do one with negative. So again, if we wanted to do 25.7, let's do this one right here. 1.49 times 10 to the negative 3. We would do 1.49. Yeah, I messed it up. 1.49 E, and then we're going to do negative 3. And that's it. You can see it automatically does the conversion for us. Moving on. Okay, what this is telling us is that on some calculators, you can put it in an engineering mode. Not all calculators have this, but what that means is when it gives you the answer, it'll automatically put it in engineering instead of scientific notation. A lot of calculators have it, some don't. But if you want to use it, it's not cheating. Only a little bit, I guess, but I'll let you have it. Alright, so in scientific notation, the number is, you're going to see quizzes like this in a lot of my lectures. Pause. Actually try to do it. It's good preparation for the test. Anyway, I'm not going to pause, because if I pause, these lectures will take forever. So, unpause me when you get it. But I'm moving on. Scientific notation. So remember, our rule for scientific notation is only 1 digit to the left of the decimal. So I'm going to count by ones. Notice it has to go to the right, because if it went to the left, well, there'd just be a lot of zeros. So we're going to go 1, 2, 3, 4. That's going to leave me with 5.6, which is 1 digit to the left of it. We moved over 4 times, so I know it's going to be 10 to the 4. And since we went from a small number to a much bigger number, this has to be small so that the both sides balance. And so we can see that it has to be answer B. And when you're taking a test like this, let's say if you couldn't remember if it had to be small or big or anything, you can immediately wipe these two out, right? These can't possibly be scientific notation because they've got more than one digit to the left. So use that to refine your choices during quizzes. Yay. Engineering notation, again, same thing. The only difference is we can only have powers that are multiples of 3, and we can have up to 3 digits to the left of the decimal spot. So I'm going to move by 3s this time. 1, well, 3 really, 6. Now look, I don't have enough digits. Remember, we can always add a 0 to the right after the decimal. And so that's going to be 560 times 10 to the 6. Again, we went from small to big, so this has to be small to balance. And that gives us this one. And again, if we were talking about, like I said before, honestly, you didn't even have to do this problem, right? None of these are multiples of 3, so I could have immediately known the answer without even having to solve it. Use the tools that you have. Metric. Okay. Sometimes students put off this. Okay, I'm going to be perfectly honest with you. I have a horrible memory. My memory is just like atrociously bad. Some people had fun getting rid of their memories. Mine was just never there from the start. I won't make you memorize a lot in any of my courses. I'm going to show you how to understand things so you don't have to memorize things like formulas. One time I'm going to ask you to memorize is right up front. We need to know these metric units. They are the way that we communicate. And so, like I said before, we don't like writing times 10 to the 3 or times 10 to the 6. Instead, we use prefixes. There are big prefixes for the positive, and there are small prefixes for the negative. Let's look at the big ones first. Down here at the bottom, we have 10 to the 3. Remember, 10 to the 3 would be how many? Well, it would be 10 times 10 times 10, which is 1,000. So most of you could probably get this one, right? 10 to the 3 is going to be kilo. I'm going to write it here, but I'm going to pull it all up in a second. Okay. Next up, we have M for mega. You might have heard of megahertz or... not a lot of mega. We got the gigs pretty fast. Oh, I gave away the next one. Next one is giga. Like gigabyte or gigahertz. Anybody know the next one? This really stinks not being in the classroom. But it is tera. And then the last one, anybody got it? I worked on a computer that had this much drive space. Peta. Also, computers are now at petaflops. So let me pull it all up. So we got kilo. Why does this do that? Kilo, mega, giga, tera, peta. 10 to the 3, 6, 9, 12. I'll be totally honest with you. These we're going to use all the time. This one a little bit less, and this one not much at all. But again, the future gets faster and more dense. You will probably need these in your career. So try to memorize these. Let's look at the small side. So we first have M. Anybody know what that is? You might know it from meters, right? Millimeters. So this one is milli. Milli. Is there one or two L's? I don't know. I stink at spelling. That's why I'm an engineer. What's this thing? Anybody know? Turns out this is micro, right? Like Microsoft. I know what you're thinking. If it's micro, why is it a U? Well, it turns out, remember, mega is capital M. Very important that it's capital. Milli is little m. And what do you know? English language only has 2 M's. Well, it only has 1 M, I guess, a big one and a small one. Instead, we use this funny-looking U thing. Again, we're going to Greek. It's mu, the Greek letter mu. So just basically make a U with like a tail in the front. And that stands for milli. No, that stands for micro. Bad professor. And then we have N for nano, like nanometer. We have pico. And we have femto. So let's pull them up. So again, remember that milli is 10 to the negative 3. Micro is 10 to the negative 6. Nano is 10 to the negative 9. Again, we will use these a lot. Honestly, capacitors, something you learn about in AC, comes in picofarads all the time. So please, please, please spend this one weekend just memorizing about 8 of these, and it'll make the next semester, this current semester, so much easier. People put this off, but all of your problems are going to be stuff like, if you have 4 microamps and 3 kilovolts, how much resistance is there? And so you need to know this right away, please. Moving on. Prefix nano means which one of these? That's right, I know you got it. It is 10 to the negative 9. Next up, pico. 10 to the negative 12. Metric conversions. So, okay, sometimes we need to go from one to the other. Like I said, if we were using our calculator, we could just ignore this and move on. But let's say you didn't have a calculator. Basically, we just need to know what this is. So what I would do is I would convert this to the form that we know it, right? That's 0.47 times 10. It's mega. What is it? That's right. 6. 10 to the 6th. So now if I want this in proper notation, we can see that that decimal has to move to the right. So let me do that. If I move this over, again, we're using engineering by 3. I have to add a 0 here. So that's going to give me 470 times 10. Now this is the tricky part. This went 3 bigger, so this needs to go 3 smaller. And so if I take 3 from 6, that gives me 3, which is kilo. That's all there is to it. Again, we can do the same thing here. This one is a little bit trickier. Let's see which way we want to get away. We've got 0.01 micro. Actually, I'm not sure why they did this. They didn't put it in the right notation, but let's see how many picofarads this is. So we got 0.01 times 10 to the micro is negative 6. If we want to know how many picofarads that is, remember pico is 10 to the negative 12. So that means I'm going to have to move this, because this is getting smaller, this needs to get bigger, and it needs to get bigger by 6. So if I'm at 0.01, I move this over by 3, and then I move it by 3 again, and that leaves me with 10,000 picofarad. So that's all there is to it. So 2,700 megawatts can be written as, well, let's see. These are all 2.7, so I know that's where we're going. Let's do it that way. So if I have 2,700, to get to 2.7, I have to move it over by 3. Let me write it all out. Times 10 to the 6 because it's mega. So that's going to leave me with 2.7 times 10 to the something. This moved by 3 and it got smaller, right? 2,700 goes down to 2.7, it got smaller. So this is going to have to get 3 bigger. So that's going to leave me with 9, which is, yes, giga. $68 kilo ohms is equal to, oh, this is a tricky one. So see, you might be saying, alright, 68 times 10 to the 3 ohms. Well, let's check the first one. If I move this by 1, 6.8 times 10 to the, again, this got 1 smaller, so this needs to get 1 bigger, 4. So that one's right. So we should just answer A? No. Because look, also B is correct. Because remember, kilo is 1,000. So 68 kilo is 68,000 ohms. And again, if we already know the answer has to be D because there's 2 of them. We can check the last one too. If I have 68 times 10 to the 3, and I want to move this, we can see to get to this, I have to move this over by 3. And that's going to give me 0.068 times 10. This, our 68, right, our 6.8 went to this, so it got smaller, so this has to get bigger. So if we go 3 bigger, that's going to give us mega ohms. And that's it. Your book makes a whole big deal about this, so I have a slide in here. It basically says either convert them both to ohms or convert them both to kilo before you do the addition. First up, the right answer is calculator. What you want to do is you want to type 10,000 plus 22E3 and be done with it, right? If you're not doing that, what I would do is I would always just convert them to base units. That way you never have to remember if it's a multi-step problem which way you went. And so the other way you could do this would just be 10,000 plus 22,000. Or alternatively, you could do, since we can see that this is 10K, right? If I move that over by 3, we could do 10K plus 22K. Whichever you find easiest. Same thing here, convert them both to one or the other, or use your calculator. Alright, this is the part students hate, significant figures. So, you need to memorize all of these rules. Well, first let me explain why we have significant figures. Do I use significant figures when I'm like calculating the tip on my bill? No, of course not. The idea behind significant figures is if we're doing important research or research that needs to be accurate, not just research, if we're doing anything that needs to be accurate, our results are only as good as the weakest tool we use, right? And so if I have a tool that can measure down to 0.000001 meters, and I have another tool that can only measure down to 0.1 meters, right? And I add the results from this, I can't say I know for a fact that my result is 2,00139 meters, right? That the final result is that accurate, because I don't really know this stuff, right? This thing here was just estimating. It said 0.02, but it could have been 0.0299999, or well, probably not that, but it could have been 0.0295639, and it just sort of left it there. So that's the reason we have significant figures, is so that we make sure we don't claim that we have more information than we do, because that can throw off other results if people are trusting that data for something. And so to do that, you need to memorize all these rules. Right after I just told you that I don't want to make you memorize anything. So non-zero digits are always considered to be significant. Zeros to the left of the first non-zero digit are never significant. Zeros between non-zero digits are always significant, blah, blah, blah. I'm going to show you a trick for this. You can memorize these if you want. I'm going to show you a trick from this because I told you I have no memory. Let me draw a picture for you here. Let's see. We go like up here, come down here, and hey, there's our house. Come over here, and I don't know, Texas does kind of something like that, and it goes up. And you can see why I'm an engineer and not an artist. Anybody know what that is? Come on, somebody say the USA. Alright, so if that was the United States of America, what would be over here? That's right, the Atlantic Ocean. And what would be over here? Yeah, I know Hawaii would be there, but what else would be there? Pacific. Okay, I keep this in my mind, right? Atlantic on the right, Pacific on the left. Now, when we have a number, let's take one. Let's say 7.521. What did I just say? Not at all what that number is. 152.71. First question we want to ask ourselves, is the period present or is it absent? In this case, the decimal point is present, so we start on, yeah, that's right, the Pacific side. See, that was why I drew the United States. So if it's present, we start on the Pacific side, which is the left side, and what we want to do is count every single number as long as it's not a zero. Basically, as soon as we hit the first number that's not zero, we count everything after that. So in this case, this is not a zero, so we count it. Once we hit the first one, we count all of them. So 1, 2, 3, 4, Why is it disappearing? 5. This number would have 5 significant digits, right? So present started on the Pacific, counted everything after we hit the first non-zero. So using our method, that has 5. And it does. So it meets, my test meets the first rule. Next up, we've got 0.0938. Decimal point is present. So again, we start on the Pacific. Remember, we count everything after we hit the first one that is not a 0. So we don't count that because it's 0. We don't count that because it's 0. We count 1, 2, 3. So this one has 3. Boom! Works for rule 2. Zeros between non-zero digits are always significant. I don't know, I'm using the Pacific method. Atlantic method, whatever. Poe method, that's what we're using. Alright, so again, decimal point is present. Start on the Pacific side. Count everything after the first non-zero. So this is a 1, we count it. Again, this is a 0, but we already hit a non-zero, so we count it. We count it, and now we have 4. And what do you know? 4, my lucky number. Next up, zeros to the right of the decimal point for a decimal number are significant. Alright, so we've got 5.100. Again, it's present. Start on the Pacific side. We count it. It's non-zero. We count it. Not a 0. We count it because we've already hit others that aren't 0, and we count it. So this one has 4. Perfect. And then zeros to the left of a whole number may or may not be significant depending on the measurement. This one's actually kind of confusing. So in this case, we actually wrote the decimal point. If we did that, we could say it had 4. If it wasn't, we could say it only had 2. You really can't know unless the person told you. Let me do an easier example. Let's say, well, 41,000 with no decimal point. We would start on the Atlantic side and we would not count it. We would not count it, not count it, count it, count it. So we'd say this one has 2. And that's it. That's all there is to significant figures. And when you're doing your homeworks and lab reports, you should try to leave it at 3 significant digits. Mainly I want to see, I'm not going to be super picky about this. But you need to remember that in real life, if you're working on precise equipment or you need your results to be accurate and matter, you need to always use significant digits. Last but not least, same sort of rule here is rounding. Now, I bet when you walked into this class, you knew how to round. You thought you knew how to round, right? Let me go back just so I have space to write. So the problem with rounding is, how do we round? Well, if a number is a 1, so like let's say I have 51. If we were rounding that to the nearest 10, we would probably round that to 50, right? Same thing if I had 52. We would round that down to 50. So we round down for 1, 2, 3, and 4. But if I had the number 55, what would we do to that? Most often on the street rounding, we would round that to 60. We would round 56 to 60, and so on. So we round up 5, 6, 7, 8, 9. Can you see a problem here? Notice that we round up more often than we round down. Again, when you're calculating the bill on your tip on your bill, not a big deal, right? Who cares? Throw in the extra penny. Or extra dollar. What am I saying? Penny. Throw in the extra dollar. Servers are doing a hard job, especially right now. But my point is, if we're doing scientific information, right, this will actually cause us to be off by a good percentage if we round often. In my research, I created simulations that had to do calculations, and they had to round tens or hundreds of thousands of times. You know, my simulation would have been off by 8 or 9%, always overestimating, had I not followed these rules. So again, this is, I haven't taught you the rules yet, but this is why we need to know how to round. In real life, the way that we round is we usually follow a rule called round to even. So 1, 2, 3, 4, always round down. just like we always have. 6, 7, 8, 9, up, just like we always have. The difference is 5. We need it so for 5, half the time we round up and half the time we round down. The way that we do that is we follow a round to even rule. So, let's take this example right here. I have 53.247. Well, that's an easy case, right? We have, because this is a 7, we would round that up to 50. Wow, why did that happen? We would round that up, let me pull up the keyboard. We would round that to 53.25. Now let's say, though, that I wanted to round it so there was only one number after the decimal point. Here's the tricky case. In this case, we would round it to 53.2. We rounded down, since by rounding it down, this number is an even number. If we had a number like, let's say, 53.35, in this case, right, I would round it to 53.4. And the reason is rounding up makes it an even number. And so since we assume that odd numbers and even numbers happen about equally, so half the time if we follow this, we'll be rounding up, and half the time we'll be following down. And so like I said, you don't need to do this for your regular lab experiments, but in real life, if you're doing information, it needs to be really accurate and precise, and you're rounding more than just once, you're doing it a lot, you really need to follow these rules. And that's it for this lecture. You've made it through your first week. We got to do the homework and stuff, and the post-lecture quiz. But after that, we're done. And we start the real material next week. We learn about atoms and electrons and voltage and current and all the fun stuff. Please learn this stuff as quickly as you can. Remember, engineering notation is simply like scientific notation with the exception that we move by threes. The exponent has to be a multiple of 3. Exponent, remember that funny thing that goes up? We call it powers. Metric prefixes, those were the kilo, giga, mega, which you promised me you're going to memorize. And scientific notation, only difference from engineering is we can use any exponent, and there's only one digit to the left of the decimal. I will see you soon. Contact me if you're confused.